Hello everyone, let's take a look at our next problem. You are given a quadrilateral with fixed perimeter and you want to maximize the area. What shape will it be? Prove it. So this is a direct, it's almost the exact same question as one we've done previously with the triangle. So of course, if you've seen that video, you know I took two different approaches. I was kind of jumping back and forth between how to do it, and one method turned out to be a total disaster. So, when I look at this question, I want to completely ignore that tedious way of trying to go about things and just try and cleverly show that the answer is going to be a square. Your intuition should probably tell you that the quadrilateral that maximizes area is going to be a square. So how do we prove it? Well, let's do something similar to what we did with the triangle question. I'm going to draw a fairly arbitrary quadrilateral here. I've drawn it. We don't need these sides to be parallel, of course. And what we did with the triangle is we fixed two of the points and allowed the third one to move around. Well, the first thing we did is we realized that maximizing area with a fixed perimeter is the same as minimizing the perimeter with a fixed area. Now with a quadrilateral, I'm having a thought that maybe we divide this shape in half so that it becomes two triangles and try and, in fact, just as I draw that picture here, if I cut this in half and think of this as two triangles, we've kind of reduced the problem to two instances of the triangle version of this problem. So if I think of these 2 points, and so this splitting diagonal is going to be fixed, using the same sort of intuition as before, if I allow this point to kind of slide around so that it is parallel to this line segment, and do the same thing with this point sliding around so that it's parallel to this line segment, well, all of those movements preserve the area of the quadrilateral, and it only changes the perimeter. Now I know that if I'm allowed to move this point around like this, then the location which minimizes the perimeter is going to be the one which lies on the perpendicular bisector of this line segment. So it'll end up being this point here. And the same thing is going to be true of this point. It has to lie in the perpendicular bisector. So by that argument, what we've shown is if I fix these 2 points, then the location of the other 2 points along these sort of I don't know what to call them, sliding axes, they both have to lie in the perpendicular bisector of the fixed line segment. Okay, and so what we can do then is we can get rid of the original diagram, and I can draw a perpendicular bisector to this line segment, and then I know that the other 2 points have to lie on that perpendicular bisector, but I'm going to draw it in such a way that they're not necessarily the same distance from this original line segment. Okay, so we have to have something like this. And then I'm going to repeat the same argument with the other 2 points. So these 2 points are fixed. I can allow these 2 points to slide around, and I know that the resulting, we have to end up in a situation where the position of these 2 points, in order to minimize the perimeter and keep the area fixed, they have to lie somewhere along the perpendicular bisector of the new fixed sort of diagonal. Okay. So after we perform that operation twice for opposing pairs of points, we have to end up with parallelogram. It could have different height and length, but we're going to end up with a parallelogram after that. So I'm going to draw 4 points. Like this. Okay, so we've got a parallelogram. Maybe I should draw this with the axes, parallel to my graph paper here, like this. Okay, I mean, it's not quite exactly parallel here, but just it's close enough, I guess. And now the obvious thing to do. Well, I guess it's not obvious if I can't state it right away, but I want to take these 2 points. I want to take these 2 points here and sort of perform an operation on those 2 points, considering these ones to be fixed, to again, what am I trying? If I minimize the perimeter but keep the area fixed, I mean, the area of this, if this side is fixed by those 2 points, and if the height of my shape is fixed, then the area stays the same. And so if I just take these 2 points and slide them left and right, but I slide them by the same amount, then of course the shape which minimizes the perimeter is going to be the one where these 2 points lie directly above those 2 points. And that's going to give me a rectangle. But I need all of these conditions to be satisfied together, where the resulting shape has to be a rectangle, such that opposing vertices lie on the perpendicular bisector of the segment connecting the other 2 vertices, and the only resulting shape there is going to be a square. Yeah, so I mean, this was a good follow-up question to the previous one. Shows that if you can sort of group one question into the same category as another, or recognize that they're very similar to a simpler question that you know how to solve, then you end up reusing the same techniques rather than going down some crazy rabbit hole like I did last time. Thanks for watching.